Deep learning for the localization and quantification of glottal gaps. The topic is based on our experience in a larynx clinic with equipment for high-speed video from Richard Wolf. The equipment automatically combines with chemography, electroglottography, attachment, and manual calculation, among others, the distance between the vocal folds in defined areas and places. The combination of measurements is optimal but manual. Tracking has been automated with deep learning. This is an improvement compared to the time-consuming process of a trained expert performing the segmentation for region of interest manually. The entire glottis has been the focus in the tracking of the glottis, as in this commercial film from Vivisys. From a treatment perspective, the specific regions of the moving glottis are of interest. There is controversy surrounding reflux in the larynx and closure in the rear part of the vocal folds. To be able to quantify a rear glottal gap would allow for evidence-based studies of this subject. The deep learning program was based on high-speed video with continuous frames, 100 during phonation of each subject video taken with a commercial setup Endocam 5562 Wolf, Germany, which records a maximum of 2 seconds in 256 times 256 pixels. We used 4,000 frames per second in a full color, recorded trans-orally using a 90-degree rigid scope on the intonation of A and with the frequency of spontaneous speech. Variations of lack of closure of the vocal folds during phonation. The mean highest relative glottal area was 15.7% and the mean lowest glottal area was 3.5%. None of the 20 subjects with a rare glottal gap had full glottal closure, as shown by the relative glottal area not reaching 0. The relative area is calculated as the glottal area divided by the left and right vocal folds plus the glottal area. The subjects' videos were selected random from a database of 17,000 high-speed films collected between 2007 and 2019 in an ear, nose, throat clinic in a medical center by one ENT specialist. 20 normal subjects' videos with normal closure of the vocal folds served as a control group and 30 subjects' videos with a rare glottal gap. 100 continuing frames from each video were used to test the post-network calculation using the open source CNN made by Failing and co-workers. Image representations of the process of localizing a specific line on the glottis for quantification. A shows the image with the biggest opening with points on the edge between the left and right vocal fold. B shows a linear regression between the points on the edges using an X over Y regression. C shows an image of another patient using a Y over X regression line. D, the collision points for upper and lower borders are marked. E, the length between the collision points is used to determine the 10% point from the rear of the glottis. F shows the algorithm loops through all segmented images and performs the same steps. G, a perpendicular line is drawn at the 10% point from the rear of the glottis. H, points at the vocal fold edges are placed on the perpendicular line to determine the distance between them and the specific point on the glottis. A single film visualizing the post-network calculations of the 10% and 50% lines from the rear of the glottis. The right and left vocal folds are marked in yellow and blue, and the glottis is marked in teal. A significant difference was found between normal videos and videos with a rare glottal gap at 10% distance from the rear glottis. Data were analyzed in a linear mixed effect model using REML, including the group glottal gap normal as a fixed effect and the subject as a random effect. N numbers of subjects, N numbers of observations. The group differences between the subjects with a rare glottal gap and the normal subjects are presented as LS, which means least squares with a corresponding 95% confidence interval. The mixed linear model was used because it is an extension of simple linear models to allow for both fixed and random effects, particularly used when there is a non-independence of the data. The SAS statistics shows a difference between the 10% lines measured in pixels. Deep learning is a major step forward in understanding the phonetic larynx because of the automation, quantification, and standardization possibilities for large amounts of information. Therefore, it was concluded that the post-network analysis can be applied for the localization and quantification of rare glottal gaps. Thank you for watching.